Hey everyone, what we'll look at today is the analysis of what we did in class. So we have our graphs here from all the different groups. You can see that we plotted the final momentum over the initial momentum for each scenario. So the total final over the total initial momentum, and it looks like every group was getting a linear trend. So the more momentum you had to begin with equals the more momentum you have to end with. And if we were very careful in our analysis and the sparks were very good at capturing our exact velocities, what we should end up seeing from the collision investigation is that our initial total momentum should equal our final total momentum. And there should have been a slope of around 1 for that investigation, meaning that for every 1 kilogram meter per second of momentum you have before a collision, you've got to have at least 1 kilogram meter per second of momentum after the collision, which again says that the momentums are the same before and after, meaning momentum is conserved. There is a change though. It's an equal and opposite change for each object. Say you had the one car coming in and pushing the other car that was at rest. The car that was coming in slowed down and had a loss of momentum, and the other car had a gain in momentum. And the reason it's an equal and opposite change, go right back to Newton's third law. If I push on you, you've got to push back on me with an equal and opposite force. So I'm going to do a couple of different examples with you with this idea of conservation of momentum to show you how to set up a problem and make sure that you account for all the motions in every scenario. So if we want to analyze the scenario from the other day when I was throwing the giant medicine ball, let's track the velocities and the masses of both objects to see how momentum is conserved in this scenario, in this kind of explosion. Right now I can tell that both myself and the ball have no momentum because we're both not moving. Once the ball is launched, I can see that the ball moves in that parabolic path and I head off in the opposite direction. You can see my position graph here is a steady decline because it's heading in the negative direction. I can highlight the information that I'm curious about and figure out how many meters per second I actually threw the ball at. And it looks like I threw it at a decent negative 3.14 meters per second. So let's watch and analyze myself. So you can see that I am moving backwards. It looks like at a pretty steady rate as I toss the ball in the opposite direction. So if we track object 2 had a slope in the opposite direction because I had positive velocity as I headed away from the ball. Give me a velocity of 1.22 for my velocity in the x direction. So let's set this problem up now and see if we have momentum conserved the entire time. So setting this problem up, there is the ball. Here is myself on the skates throwing the ball, and initially the velocity of the ball and the velocity of the person were 0. So if I want to conserve momentum here, I've got to say that my momentum in the beginning must equal my momentum at the end. And remember, momentum is a vector quantity. So if both objects are together, I could say that mass of the ball plus mass of the person multiplied by our combined speed in the beginning must equal the ball heading off in the negative direction and myself heading back in the opposite direction. So the ball headed negative and I headed in the positive direction. So when we do that, we can say mass of the ball, velocity of the ball, final, plus mass of the person, velocity of the person, final. And we're going to set that up. So we want to make sure we know the values. That was our 30-pound ball, so it's about 13.6 kilograms for the mass of. For myself, I have about 77 kilograms of mass, so we should expect the ball to travel much faster than myself. We saw the ball travel around 3 meters per second in the negative direction, and the graph said that I was moving backwards around 1 meter per second. So let's solve for my speed. Let's see how close the video analysis got to what we should get. The ball has a mass of 13.6 kilograms and went backwards at 3.13 meters per second. I know my velocity, and my mass was 77 kilograms, and I'm trying to solve for my V final. Crunching in your numbers there, let's do some work, and you get this half of the equation to equal 0, since we had no momentum in the beginning. 13.6 times the 313 comes out to 42.5 kilograms meters per second. Now equals my momentum of 77 multiplied by VF. So I'm going to divide by my mass, and I should get a final velocity of 0.55 meters per second, which is a lot different than how the video analyzed me. The video said I was going twice as fast. I was going about 1.2 meters per second. And I think a couple things may have been happening in that demonstration. Instead of just me keeping my feet rigid the entire time, as I pushed, I widened my feet and I actually took kind of a hockey skate backwards to allow myself to start moving. So if I truly just stood still and threw, this would be the true speed that I would have to end up with. We can try to analyze that again in class to see if we get a much closer value. But that should be my predicted speed. I think I had a little bit of alterations with the way I moved my feet after the throw. But that's how you want to set up a conservation of momentum problem. Let's try another one. So if we look at this simulator here, we can set up any collision that we want. We can put in the masses, we can put in the velocities, and what they'll do is they'll spit out what happens when the objects collide with each other. In this nice example, there are no frictional forces like I was experiencing with throwing the medicine ball, and we've got a different way of setting up collisions. We can set up the collisions as elastic or inelastic, and we're going to have to define what that actually means to be elastic or inelastic. But let's set up these two sliders here. Let's say we have the orange mass being 4 in its mass, so it's much bigger than the blue cart, and it's moving with a velocity of, say, 2. So the initial momentum of the orange cart is around 8 kilograms meters per second, and for the blue cart, we're going to make it a mass of 1 and a velocity of 0. Let's let the collision happen. And there's the after part of the collision. So after the collision's over, you can see that the orange mass is now still heading to the right at 1.2. It lost a little bit of its velocity. The blue cart has now picked up a lot of velocity. 3.2 is its current speed. So let's show that that momentum must be conserved. So here's before the collision. Orange cart was flying in at a velocity of 2 meters per second. It has a mass of 4 and a velocity of 2. If I want to calculate its individual momentum, I'll take m1 times v1, which gives me 8 kilograms meters per second. And I'm going to add that to m2 v2. In this case, m2 is 1 kilogram, but the velocity is nothing. So we're going to cancel out that quantity altogether. Since momentum is a conserved quantity, we want to make sure that everything on the back end matches up. So we can see that the orange cart was heading off at 1.2 meters per second, and the blue cart was now heading at 3.2 meters per second. Same setup on the after the collision. You're going to take mass 1 final times v1 final plus mass 2 times v2 final. And the first, for mass 2, it's going to be easy. It's 1 kilogram times 3.2, or 3.2 kilograms meters per second. And for the other mass, we're going to take our 4 kilograms and multiply by 1.2 meters per second. What that gives us is about 4.8 kilograms meters per second. So 4.8 plus 3.2 gives us exactly 8 kilograms meters per second. So momentum is conserved. Let's try that again and set it up as inelastic. Same scenario, but now inelastic. You can see in the inelastic collision here, the two objects hit and stick together like you did in the lab. So when that happens, both will be moving the same velocity at the end there. So that 8 kilograms meters per second of momentum in the beginning has to equal the 8 kilogram meters per second at the end. So now everybody's moving at 1.6 after the collision. So if we want to find the combined momentum of both objects, you can just combine their masses. Mass 1, mass 2, times their final velocity. So their combined masses here end up being 5 kilograms Multiplying that by 1.6 gives us 8 kilograms meters per second in the end. So the momentum before does equal the momentum at the end, whether it's an elastic collision or an inelastic collision. But let's analyze that a little bit further. Due to the law of conservation of momentum, total momentum of a system can never change. It's always going to be the same before and after. Momentum initial must equal momentum final. And since momentum is a vector quantity, we need to make sure that all components are conserved. Whether it's x, y, z direction, momentum must be conserved in all directions. And the way to know what's going to happen in a collision, whether it's elastic or inelastic, is you want to analyze the kinetic energies of the objects. Momentum will always remain constant in every collision. However, energy can change. We could use energy to see if there's anything lost to the system, if there is heat, if there is sound, if there's a dent in the car once they hit. The momentum will always equal, but energies not necessarily have to be. So we've got 3 different types of collisions here: elastic, inelastic, and then there's the perfectly inelastic. Elastic collisions are when your total momentum and your total kinetic energy all will remain the same. So to analyze a collision, do your momentum conservation. Find the velocities before and after and make sure the momentums are the same. To then see if it's elastic or inelastic, conserve the kinetic energy. And if the kinetic energy do not equal before and after, then we say the collision is inelastic. Inelastic doesn't always have to mean stick, it just means that energy is lost. And a perfectly inelastic is what we did in the last scenario. That is when the collision happens and the objects stick together. There is no way that when 2 objects hit and stick, there is no sound made, deformations of bumpers. Energy will be lost in perfect inelastic every single time. Inelastic are pretty much what every other collision you see when 2 objects run into each other. And elastic, the only elastic collisions that we're pretty sure exist are between like air molecules, that when they run into each other, they conserve both their energy and their momentum. So those are the 3 different ways you can define in a homework problem. Make sure you show me that the problem is elastic or inelastic based on energy conservation. Collisions happen everywhere. They happen in NASCAR when 2 cars run into each other. They happen when 2 trains collide together. They happen when 2 cars crash. Momentum is conserved in every single collision you ever see. What won't be the same, like you can see there, is that work was done to dent those bumpers and energy will be lost. Here you've got an astronaut catching a book. The astronaut's at rest, catches the book. Since the book had momentum, when the astronaut catches it, both of them now must conserve that backwards momentum and have the same momentum before and after. So there's many collisions that we can have. You can have collisions in all directions, all types, whether the objects are moving in opposite directions, they are hitting and sticking, they are together and then explode apart, like when I threw the medicine ball. And when I say explosion, I don't mean an actual explosion. I could mean just a mechanical explosion, as me throwing the ball away from myself. Or go back to the space station scenario. If I was at the space station and my rope broke, we'd said let's throw the hammer in the opposite direction. We compared that to Newton's third law, but now let's compare it to momentum. If you look in the beginning here, there's no momentum for the panel or the astronaut. If the astronaut throws the panel in one direction, that 0 momentum must remain the same for the whole system. So if the panel has negative momentum, the astronaut must have positive momentum. And this is exactly how rockets work. They throw mass in the opposite direction. Conservation of momentum, we have to have mass move in the opposite direction. So you don't need to push on the air, you don't have to do anything but throw mass away from you to make the rocket move. You don't even need gases. If you just stuck your hand out outside the rocket and started throwing baseballs in the opposite direction, you would give yourself propulsion. So rocket science is no more than conservation of momentum, just like the scenario you're about to see tomorrow.
Go ahead, just run as fast as you can.